Good morning. My name is Victor Santos. I am a PhD student at the group Confirmation and Measured Phenomena, and my advisor is Jonas Mazier. Today I'm going to talk about continuation to the previous work I presented here, which is really an experimental approach to the algorithm I developed presented in the last seminar, and it's called Entanglement-based prime detection by IBM Quantum Processors. So, to summarize what I did in the last seminar, we developed a quantum algorithm that identifies prime numbers within some interval, and it pretty much starts like codification, where we have number q of qubits and two systems, and we have system A and system B, each of the dimension p, and we have this mapping to qubits to this big part of the system. And after that, we go to the quantum computing part where we develop quantum circuits. I'm not going to details here, but in the green part, we have the preparation of the initial system. Here we get the simplest one and the one we are focusing on this work. The purple part is preparation of the voltage states according to the evolution operator. And the yellow part is the part where we measure the entanglements of the part of the system, specifically system A. Then, when we do this for a period of time, we can estimate using Fourier analysis the Fourier modes, where we have this codification of prime numbers. Specifically, when we do that, first we obtain entanglements such as this. And you can see we have two types of curves, the analytical and the simulation. We can barely see the difference because there is a simulation, so it looks really good here. From that, we use, as I said, Fourier analysis to integrate to obtain this type of graph. And this is where we can actually make the use of the algorithm. So, to recall what I introduced in the last seminar, the green line is the line where in this interval there's prime numbers to belong. So each one that belongs here is a prime number, and each one above is a composite number. And this is what I presented in the last seminar. Now, when we go to a real computer, things get really much more complex. So I'm going to talk about some details to make sense to improve and make sense the results I'm going to present later. So one of the biggest problems today in quantum computing when we try to make an experiment or a demonstration is a phenomenon called decoherence. Here I have an image that explains in a really simple way. So when you have a classical scattering and you have, say, a particle, this orange circle, if we throw, say, a photon, on average, it does affect the motion of this state and the motion of this particle. However, when we go to the quantum realm, things get different. So we think of this, say, this photon as a part of the environment interacting with the system. And if the system is coherent, that is, it exhibits interference patterns in quantum behavior, the photon, when they reach this particle and leaves, it takes part of this coherence with itself, and they become entangled, which means in the end that we lose the information of the system on its own. We lose because now the system is entangled with the environment. So this is really similar to what we think as losing energy when if to the, say, pushing a block in the ground, but in fact the energy not lost, it's just provided to the ground. So really similar. So in quantum processors such as the one in IBM, this is one of the main problems we have when we want to extract results. So to illustrate, we have, say, qubits, this state, like the matrix with one path in every entry. When we have a really strong in the coherence process, it turns out this matrix becomes this diagonal matrix, and we say that we lose the coherence because the off-diagonal terms start to decrease. In this strong case, it turns out to be zero. So this is pretty much what happens when we go to quantum computers, one of the main issues. So the IBM hardware, we have used two types of chips. First, we did 4 experiments, and one of them is Marrakesh, is where started with this, and then the other 3 we use Aki. Because Marrakesh turns out, we found out it to be not that good. And this, I don't know if you can see, but we have this 2 and 1. Basically, the start of 2, it's the time where a system, when you apply operations, it stays in that state. So what I said about here is the time. The bigger this time, the better. And 1 is the time where when we make a system reach an excited state, it is the time where the system stays that state before it decays to the ground state. So you can see that both times are lower than the Aki chip, and this is the topology of each of these circles is a qubit. You can see the blacker the color of the qubit, the better the quality. So you can see this chip is in general much worse than one. Here's just a part of the code where how we do it in Python. As I said, Aki is the main one we use. We have this part where it's a technique really with pulse that IBM uses to average the noise to 0, not really relevant. This part is where we define the quantity that I showed in the previous slides. And here we have another part of the circuit where it transpires the circuit, which means it simplifies gates. And we use optimization level 3, which makes even things better. So this is the configuration that is important that we use in IBM. And when we go to, well, as it would be clear, initial states are really relevant in the work. So as I said, we have an AP system, which same methods of probability. And the one we are going to, even though I'm going to show both, the one we are going to focus is this one, which is more simple and easily prepared. More easily preparable states. But we have also this very coherent state, which is really much more complex. And when we introduce the coherence process and the fact that this is present in today's quantum computers, we have to use mitigation techniques for errors. And one we found out to be really good that we introduce as well. It makes sense. We have the theory that predicts the arguments is given by that. So you can see that only depends on the initial states and amplitudes. Then we extract the theoretical Fourier modes. However, when you go to the measurements, we have in our system, we have an oscillative pitch where we measure its state and we estimate this zero parameter, which is the probability of the qubit being the zero state. So we estimate the same function through different approaches. Then we use the integral to obtain the estimation of the Fourier modes. So we found out that this protocol is really cheap, which is really important in this subject. That first, we can obtain the theoretical one, at least for a few dimensions, and the experimental ones. And we find out that if we define a new Fourier mode by multiplication, a global multiplication, gamma that depends on the dimension, we see that we can improve the results by using some maximization technique of the definition of Fourier modes to the analytical ones. So we define the sum, and the minimization gives optimized gamma factor, which is going to be shown later in the results. And one thing that I did talk about in the last seminar, which is now relevant, is the tolerance. How do we know if we have errors in the results? How do we know how reliable is the points we are obtaining? So we did this for the uniform superposition, like I said, the focus of this work. I'm not going into details here, but when we do the calculations, the direct calculations, we can show that if for an integer n that is a prime number times itself, b, it is possible to show that it is actually, for composite number, it is a bound. So we can always expect the results of our modes for composite numbers to be equal to this in general or bigger. There is some minor detail that for n bigger than t, sometimes some integers such as 2 times a prime number, 3 times a prime number, can violate, but no other integer can violate. So in practice, we have a lower bound for composite numbers. As you can see, this is in fact what we show here. So as I said, we have 4 experiments. As I said, my cache is the only one we did for the spin coordinate states. So to make things clear, so we start same shape stacking. We have 2 dimensions. The points, the number of points integrated to user 30 and 120. And we have this correction factor of the gamma given by this 1.26 and 1.73. And as I said, even though we multiply the for modes, you can multiply the curve of entanglements, maybe this orange curve. You can see when we multiply this by this vector, it really gets much closer to the analytical curve. And this strip is a strip where we apply that condition where if they are below this curve, we must try to divide it by 2, 3, or the discrepance of n. And we find out, for example, in this case it works perfectly. Here more not easy as visible, but it works as well. The only ones is this one, 9 and 14, which are below. So 9 is visible by square, and 14 is visible by 2. So the criteria works perfect. We didn't apply this with pre-recurrent states because, as I said, we did different shapes. It doesn't translate when we want to use this criteria. And turns out we are currently doing higher dimension experiments, and this state is not. We don't know how to prepare it for higher dimension. So this is why one of the reasons we are not focusing on it. In the next. We are doing, as I said, higher dimensions and trying out mitigation techniques. But we think our technique is going to be the one we are going to use mainly. That's it.